welcome to week 3. This is module 3, Evolution of Hawaiian Volcanoes. Today we will go over tectonics and their role in creating volcanoes. We will focus specifically on hotspots and the evolution of Hawaiian volcanoes. As you recall from last week's lecture, we talked about the layering of Earth's interior. This image here describes the composition as well as the physical characteristics of each layer. For example, if you recall that Earth's interior is composed of a solid inner core, liquid outer core, both of which are rich in iron and nickel. The mantle is capable of really slow movements due to convection, and this is how magma plumes transport magma to and through Earth's crust and recycle magma at depth. The mantle is said to be plastic or ductile, while the crust is solid, cold, and brittle. When we begin to discuss tectonics, the Earth's layering system becomes further divided. If we look at the right side of this figure, we see 3 new terms are introduced: the lithosphere, asthenosphere, and the mesosphere. The lithosphere is composed of the upper mantle and the crust. The lithosphere is rigid. The lithosphere is broken up into a series of plates. The lithospheric plates sit upon a partially molten layer of rock known as the asthenosphere. The asthenosphere is composed of the upper mantle and may extend to 150 to 300 kilometers depth. The asthenosphere is said to be plastic or ductile. The lithospheric plates move via convection, which we will discuss further in subsequent slides. As you can see here on this map, 13 major plates have been identified. Hawaii sits in the middle of the Pacific Plate. Other major plates include the Nubian, Arabian, Eurasian, Antarctic, Indian, Australian, Philippine, South American, North American, Cocos, Nazca, and Caribbean plates. There are also several smaller plates in places where 2 plates run into each other. And in places where 2 plates run into each other, mountains, volcanoes, and deep-sea trenches may be formed and earthquakes may occur. If we take a look at the age of the oceanic lithosphere, we see in the image here that blue colors represent older material, up to 180 million years before present, while red colors represent newer material. We see that new material is created at ocean trenches, where 2 plates are spreading or moving away from each other, and magma is welling up from the mantle. Plates are also recycled into the mantle at subduction zones. So if we look at this figure here, again, we see that at spreading centers, where 2 plates are moving away from each other, new crust is created as mantle rises up towards the surface. And at subduction zones, as you can see here, old crust is destroyed or recycled back into the mantle. So spreading centers, new crust is created. Subduction zones, old crust is recycled or destroyed. If you recall, at a subduction zone, the denser plate dives beneath or subducts beneath a less dense plate. For example, the more dense oceanic plate would be subducted beneath a less dense continental plate. This process is said to recycle cool, rigid oceanic crusts back into the mantle. This process generates a series of shallow earthquakes, shown here by stars. So again, at subduction zones, old crust is being recycled. Taking a closer look at the Tonga-Kermadec region, here the Pacific Plate is being subducted beneath the Australian Plate. The colors in the figure represent the focal depth, or the depth below Earth's surface, where you would find a hypercenter of each earthquake. The yellow colors are the deepest, and the cyan and blue are intermediate, while the red and brown colors are the shallowest earthquakes. The small gray triangles, shown here, are volcanoes that are produced by this process. In addition to generating earthquakes, subduction zones also produce volcanoes. And I showed you this figure again last week in Module 2. So at subduction zones, magma is being generated via hydration melting. As the oceanic lithospheric plate is subducted beneath the continental plate, volatiles are released by heating the wet plate and sediments. This results in a zone of partial melting, shown here in the red, yellowish oval. Magma formed as subducting plates slowly rise into the overriding crust and finally to the surface, forming a volcanic arc, a chain of active volcanoes which parallels the deep ocean trench. Beneath the active volcano or volcanic arc lies intrusive igneous rocks formed from magma that didn't make it all the way to the surface before crystallizing. The volcanic arcs may also be volcanic islands or volcanic island arcs, such as the Aleutians and the Marianas Islands, and this occurs where one oceanic plate subducts beneath another oceanic plate. Or continental volcanic arcs, where oceanic plates subduct under a continental plate. The most abundant igneous rock formed at volcanic arcs is andesite, though volcanic arc rocks may range in composition from basalt to rhyolite. Although the surface of the Earth is solid, its interior is soft and flows like a very viscous fluid. This flow is called mantle convection. We talked about this briefly last module. Mantle convection is an important method of heat transport within the Earth. Mantle convection is a driving mechanism for plate tectonics. I will repeat that. Mantle convection is a driving mechanism for plate tectonics, which is the process ultimately responsible for producing earthquakes, mountain ranges, and volcanoes on Earth. If we take a look here at this image, we see different colors represent variations in temperature within the mantle. The black region in the center of the image is the core. The red and orange colors represent hot temperatures, implying that that material is rising through the mantle. The hot pipe-like structure in the center, shown here, is an example of a mantle plume. On Earth, mantle plumes are thought to produce volcanic features such as the Hawaiian Islands. Blue and green colors represent cold temperatures, implying material is sinking back into the mantle. So here we have this recycling process. These cold regions represent the subduction of lithospheric slabs on Earth. The temperature difference between the hottest and coldest material is about 1500 degrees Kelvin. The rising and sinking motions deform the outer surface of the planet, shown in gray, and this represents surface topography. The gray regions shown in this image are shown with considerable vertical exaggeration. The actual topography caused by this process is only a few kilometers in amplitude. If we take a look here at this image of the Hawaiian hotspot, we see that seismic tomography is used to study the internal structure of the Earth. This allows us to better understand plumes or the movement of magma from the outer core to Earth's crust. This diagram shows how seismic waves from distant earthquakes pass upwards to Hawaii seismometers, shown here in these white lines. If they pass through hot rocks, such as a hot spot, they are slowed and they arrive late, such as the region that passes through the plume head. Here is a map of the major hotspots on Earth, shown by the red dots. As you can see, there are quite a few. While the majority of hotspots are located in the middle of oceanic plates, there are a few that are located on continents. Where hotspots occur in continental regions, basaltic magma rises through the continental crust, which melts to form rhyolites. These rhyolites can form violent eruptions. For example, the Yellowstone caldera was formed by some of the most powerful volcanic explosions in geologic history. And you may be surprised to know that Yellowstone is actually formed by a hotspot. Now, if we focus more specifically on the Hawaiian hotspot, we see here that Hawaii is located in the middle of the Pacific Plate, shown in pink. The Pacific Plate is moving towards the northwest, so it's moving in this direction. For a long time, scientists were boggled as to how islands could have formed at the center of a lithospheric plate. In the next few slides, we will learn how volcanoes form at hotspots. A hotspot, as we know it, is an upward moving, in simplified terms, a hotspot is an upward moving cylinder of solid mantle material, shown here on the left. The material in the center moves the fastest and therefore finds itself out of equilibrium the most. In turn, it melts to the greatest degree. Volcanoes fed by this part erupt tholite basalt and erupt often. The outer part moves the slowest and only melts a little bit. Volcanoes fed by this eruption region erupt alkalic basalt and erupt infrequently. Tholitic rock types tend to be more enriched in iron and less enriched in aluminum than cal-alkaline rock types. If we look here in this image, we see that the various volcanoes on Hawaii Island are represented by triangles. The green arrow represents the movement of the Pacific Plate. The Pacific Plate is moving northwest at about 9 centimeters a year, so very slow. Volcanoes fed by high magma production, such as Mauna Loa and Kilauea, erupt often. They are located in the center of the cylinder, whereas volcanoes fed by lower magma production or on the outer regions of the cylinder, such as Mauna Kea and Hualalai, erupt less often. Kamaʻehuakanaloa, formerly known as Lo'ihi, is just moving into the high production stage. In reality, if the upwelling starts at the core mantle boundary, then a hotspot is more than 10 times as tall as it is wide. You can see in this image that each of the volcanoes are labeled and that age increases from right towards the left as you move from distance from the hotspot at Kamaʻehuakanaloa. So the volcanoes here on Oahu, if we were to just give an average age for the two volcanoes for the Waianae Mountains as well as the Ko'olau Mountains, they're about 3.4 million years old. Whereas Ni'ihau and Kauai, which are much older and located further towards the northwest, further away from the hotspot, are about 5.6 and 4.9 million years old. Here in map view, we can view the Hawaiian Ridge Emperor Seamounts chain, which extends for some 6,000 kilometers from the Big Island or Hawaii Island here in the east to the Aleutian Trench off of Alaska. The oldest dated volcano near the southern end of the Emperor Seamount chain is 81 years old. The bend between the two chains here is dated at 48 million years old. Volcanism on Kauai Island ended about 3.9 million years ago, making it the oldest of the main Hawaiian islands. On the island of Hawaii, the youngest of the main Hawaiian islands, Kilauea and Mauna Loa, are historically the two most active volcanoes with frequent eruptions. The submarine volcano, Kamaehua Kanaloa, formerly known as Lo'ihi, off the island of Hawaii's southeastern shore, is the youngest volcano of the Hawaiian Ridge. The Hawaiian Islands themselves are a very small part of the chain and are the most youngest islands in the immense, mostly submarine mountain chain composed of more than 80 volcanoes. The length of the Hawaiian Ridge segment alone from the Big Island northwest to Midway Island is about equal to the distance from Washington, D.C. to Denver, Colorado, about 2,600 kilometers. The amount of lava erupted to form the Hawaiian Emperor chain is calculated to be at least 750,000 cubic kilometers, more than enough to blanket the entire state of California with a layer of lava roughly 1.5 kilometers thick. A sharp bend in the plate here indicates that the motion of the Pacific plate abruptly changed about 43 to 48 million years ago, as it took a more westerly turn from its early northerly direction. So you could see initially when the Emperor seamounts were formed, it was the Pacific plate was moving more north. However, about 43 to 48 million years ago, there was a shift to a more west or northwest direction. Why the Pacific plate changed direction is not known, but the change may be related in some way to the collision of India into the Asian continent, which began about the same time. We are going to walk through this diagram over the next couple of slides. We're going to go through it slowly. The diagram below shows the life stages, or the evolution, of a Hawaiian volcano. Note that because of the subsidence, about half of the volume of the volcano is below the level of the ocean floor. Within the main southeast Hawaiian chain, Kamaehua Kanaloa, formerly known as Lo'ihi, I hope you guys are now realizing the name is no longer Lo'ihi and becoming more familiar with the name Kamaehua Kanaloa. Kamaehua Kanaloa is in stage 2, so it's still a submarine volcano. Kilauea is a young stage 4, and Mauna Loa is a mature stage 4. So they're in the main shield building stage. Hualalai and Mauna Kea are both in stage 5, so post-shield stage. And Kohala is in stage 6, beginning to experience erosion. Moving to Maui, East Maui is in stage 7, whereas West Maui is between stages 7 and 8. East Molokai is also in stages 7 and 8, and Lanai, which skips stage 5, Koho'olave, and West Molokai are in stage 6. On Oahu, the Ko'ola Mountains are still in stage 7, and Waianae is probably between stages 7 and 8. Kauai and Ni'ihau are between stages 7 and 8 as well. As you can see, even though a lot of work has gone out to figure out this sequence, the volcanoes themselves have a good deal of variation and haven't perfectly followed the sequence. So now we're going to walk through this diagram and talk a little more specifically about the different stages. Looking at the life stages of Hawaiian volcanoes in more detail, the pre-shield stage initiates volcanic growth, so stages 1 to 3. The initial stage of volcano growth is a submarine pre-shield stage characterized by infrequent small volume eruptions. Lava that erupts underwater builds pillow lava and constructs a steep-sided volcanic pile with a small summit caldera and 2 or 3 rift zones radiating from the summit. Calderas continue to develop and fill repeatedly throughout the pre-shield and shield stage and go hand in hand with the high rate of magmatism that builds the Hawaiian Islands. The pre-shield stage lasts for about 200,000 years, yet produces only a small portion of the final volume of the volcano. As the volcano grows, composition of lava changes, and eruptions become more frequent and voluminous. When the transition is complete, the volcano enters the shield building stage. The only current example of a pre-shield state volcano is Kamaehu a Kanaloa. And chemical analysis of rocks collected during submarine dives using ROVs to Kamaehu a Kanaloa show that the eruptions are transitioning to the subsequent shield building stage. The shield building stage is the most productive volcanic stage. More than 95% of Hawaiian volcanoes' volume is erupted during this stage, which may last up to 2 million years. The oceanic crust of the Pacific Plate, unaccustomed to the enormous weight of the volcanoes building atop it, subsides greatly during this stage, as much as 3 millimeters per year, based on current subsidence rates recorded on the island of Hawaii. Early shield building eruptions are entirely underwater, but the rate of growth exceeds the rate of subsidence, and eventually the volcanoes emerge above sea level. Mauna Loa and Kilauea, two volcanoes shown here in these images, are in the shield building stage. It's unknown exactly how long Mauna Loa has been producing shield stage lavas, but the earliest pre-shield flows erupted on the seafloor between 0.6 to a million years ago. Kilauea transitioned from the pre-shield stage about 155,000 years ago. Post-shield stage eruptions are the next stage, shown here by number 5. And this stage really just caps the volcano with lavas, but these rocks form only a small part of the total volume of the volcano. Not all Hawaiian volcanoes go through this stage. For example, the Ko'ola volcano on Oahu and Lanai volcano did not, whereas other volcanoes have erupted thick post-shield lava sequences. For example, the Waianae volcano on Oahu and Mauna Kea volcano on Hawaii Island. During this stage, high lava fountains produce large amounts of cinder and short, thick a'a flows that steepen the slopes of the volcano as they pile up near the summit and rift zones. These lavas commonly fill and overflow the shield stage caldera. During the post-shield stage, the eruption rate decreases to 0, typically within 500,000 years, but this stage may continue for as long as 1,000,000 years. Following the post-shield stage is a period of erosion and subsidence, during which deep canyons may form along the flanks of the volcano as the volcanic islands erode and subside. Next, we'll move on to stage 7, rejuvenation. And this stage, eruptions typically following a long, quiet period. So this is the final stage of active volcanism, stage 7, rejuvenation. Periods of erosion may precede or be interspersed with the rejuvenated stage. Lavas commonly erupt through the reefs that form offshore as erosion progresses. Eruptions that occur near the shoreline produce volcanic maars, and eruptions further inland form lava flows that funnel down eroded stream valleys. A rejuvenated stage activity has low eruption rates and may occur over several million years. Eruptive features on Ko'ola volcano on the island of Oahu are classic examples of rejuvenated stage volcanism. The most iconic example is Diamond Head Crater, or Le'ahi in Hawaiian, which is about 400 to 500,000 years old and is located east of Waikiki Beach. Lavas erupted during the rejuvenated stage are also abundant on the islands of Kauai, Ni'ihau, and Molokai, as well as West Maui. We're going to have a field trip later in this class, a virtual field trip, where you will take a closer look at some of the rejuvenated volcano features on Oahu. Following the rejuvenated stage, a long period of erosion and subsidence eventually reduces the volcanic islands to sea level. Basalt is a porous rock that easily succumbs to erosion, especially with the high amounts of rainfall in Hawaii. Erosion processes include gradual degradation due to weathering and massive landslides that displace large parts of the island. We will discuss in a future lecture specifically these large landslides and some examples of places across Hawaii that have experienced them. As the volcanoes erode and subside, they become coral atolls like many of the islands in Papahanaumokuakea. And we're also going to have a lecture in the future that looks specifically at atolls and coral reef islands. Now, if we take a look at this table, we see that this table shows the names of each volcano across Hawaii, with corresponding ages listed under the names of mapped geologic units in red. Note that not every volcano has every stage. Some volcanoes skip a stage, for example the Ko'olaus, and some volcanoes die young, like Lanai. Here in this picture, we see the volcano named East Molokai. Early Western geologists noticed the color and thickness varied in the layer of volcanoes. Later, geologists determined that there was a geochemical pattern as well. At East Molokai, we see at the base there are thinner layerings that weathered to red-brown. This represents the main shield tholite flows. Tholite flows are iron-rich and will oxidize or rust, giving it the reddish color. Above this layer is the pole shield alkalic flows. Layering is thicker and rocks will weather to gray and light gray. Here in the green, you see the surface of the old volcano. All right, so that is the end of lecture 3A. Now would be a good time to take your quiz 3A, and as just a reminder, there will be one more lecture, lecture 3B after this that also has a quiz.